Let's consider right now the extension of Bernoulli's theorem for a real fluid. So, before we have seen how to define the total head in a point where you have inside your direction of the fluid a turbine, so basically machine that takes a part of the energy associated with the fluid and they convert this energy, so they decrease the original energy of the fluid, and because they convert this energy to electrical one, and pumps which give basically the energy to your fluid. Let's assume right now that we are not considering anymore an ideal fluid but a real one. And the real fluid is characterized by the fact that there are some energy losses associated with exactly the nature of the fluid. So basically, again, if I move from a point 0 to a point S inside the direction of the flow, in the case of real fluid, you have also to consider the decreasing associated to distributed energy losses, which are losses linked to the nature and of your fluid and the geometry of your pipe, times the S, because they are integrated over the direction of the fluid, minus a kind of losses related to the geometry of your fluid. So they are what are called concentrated energy losses. Basically, these first losses, you can see them along your pipe, while these concentrated energy losses are linked to changing in geometry right here or right there, or for example, if along your pipe you see elbow, restriction of cross-section area, and other kind of different geometries. So let's consider this picture. You are moving from this tank to this one, and the total head changes because from this one to this one, basically you have a lower energy. If the fluid is ideal, you can see this situation represented in the red line 1 and 2. So the energy line remains constant and the piezometric line is constant, but translating of a quantity exactly equal to the cinetic eighth. In the case of real fluid represented by the blue line right here and there, you can see that moving along your pipe you have basically some decreasing in your total energy, and these decreasing are exactly what they are called the distributed energy losses. We will see in the next lesson that this J, which is the hydraulic gradient, and basically it's the variation of your total head along the motion of your flow, is something related again to the nature of your fluid and to the geometry of your pipe. This thing right here again is linked only to the changing in geometry of your fluid. So, in the real fluid, you have a decreasing in the total head, so the total head is not constant anymore, and again a decreasing of your piezometric head, because the piezometric head is the total one minus V to the power of 2 over 2g. Let's see two simple cases. The first one is a system with a turbine. So again, the turbine is a machine that takes part of the energy associated with the flow, and this part is exactly this delta H, and converts this part of energy in other kind of energy, like exactly the electrical one. So basically, we can define that HA, so the total head associated with the first tank, minus the total head associated with the second tank is exactly Y, so the available difference head. At the same time, before and after your machine, you can measure HM and HB, which are exactly the difference, the decrease of energy due to the presence of the turbine. Alright, so let's try to compute Bernoulli's from tank number A, tank A, to the point exactly above before the turbine. In this case, you will have so that HA, then for example, in this case, we not consider right now the concentrated energy losses. So we move from this point to this point right there. So again, we will have that HA minus distributed losses, so minus J1L1, are equal to HM, so the total head before your turbine. Alright, the same we can do it for the total head after your turbine, and this will be, the total head will be HB, so the total head in tank number B, plus alpha, then Coriolis coefficient alpha to that multiplies V2, so the velocity in this section right here to the power of 2 over 2g, and this one is combined with again J2 plus times L2, so we'll have HB plus the kinetic height plus J2L2 is equal to HB. Then delta H, which is the decrease of energy due to the turbines, is given by exactly HV minus HM minus HB, so the head before turbines minus the head after the turbines, which means that is equal to Y minus the energy losses. I would like to show you if I can. I would like to show you another way to compute this stuff.